All right, so we're going to talk about how to take triple integrals with cylindrical coordinates. First, what are cylindrical coordinates? In the same way that polar functions are just a different way to define a function, right? Usually in Cartesian, we say a function, right, y equals f of x. For a certain value of x, you get like a certain value of y. That's a function, right? With polar coordinates, it was like, okay, you input a certain, it's, really should be theta, but like basically the idea is that, with polars, it's like you input a r value, and then I feel like it makes more sense to like input a theta value. But the point is like for a value theta, there is a value r that is assigned, right? So that's kind of like a polar function. R as a function of theta. Yeah, you input a theta and then you get an r out of it, right? And then you can make kind of these polar curves, right? Where, for a certain value of theta, the r changes. Now, cylindrical coordinates input both an r, which kind of acts like a radius, right? Or really distance from the origin, right? Radius is more of a term used with circles. But you input a certain distance from an origin, you input a theta swept out from the x-axis, that's kind of the important part, and you get a certain z value. And what you can do is you can imagine we can express functions. Let me use a different marker because this marker is looking kind of dead. We can express functions in terms of cylindrical coordinates. So we can kind of say, okay, the way to bridge over, we kind of say that, hey, x squared plus y squared equals r squared. Hopefully you can see that, right? Because I'll make it bigger. Hopefully you can see the Pythagorean theorem. If this was my xy coordinate in regular rectangular coordinates, then r just represents, the square of r is just x squared plus y squared. We can say then that r, and just to kind of show you, if this is xo and this is y initial, it makes a right triangle. So Pythagorean theorem applies, and we could say, hey, x init r times sine theta is equal to y, r cosine theta is equal to x. And we can kind of bridge over from cylindrical to rectangular and vice versa, right? So hopefully this is not like a crazy idea. We kind of worked with this in polars. Now we can use it to take triple integrals. And the intuition is that if you were to have some sort of region, and with this region on the xy plane, there will be some sort of surface on top, and then you kind of create this volume, and then I should really make this dotted. But dv, right? If we think about what this dv represent, well, what we can do is we can divide this kind of from the origin. If we take this little polar area, right? So if we take this area and multiply it by the height, this kind of slice, this very thin slice where this represents d theta, and this represents, d theta, and then this kind of length represents r, then you can find the area and then do base times height. So we would get dv is equal to the height, which is really just, I have to think this through. Okay, how did I derive this? Oh, okay, wait, I see, really, because this isn't really like a flat slice, really you would have to take like a slice, a very small kind of section here with a height dz. So I would get dz times the d area, and we know dA is just r dr d theta, right? Because if we think about a small little section right here, which represents this would represent dr, and then this sector right here would equal r d theta, right? Whatever the r is at that point. So it's the same idea of just splitting it into lots of teeny tiny boxes, and we would get that dv, which I should make capital, dv equals r dr d theta dz. And you can rearrange the order, right? So let's go ahead and do just some examples. 2 examples. That's all I really need to do, because this is just another strategy to do triple integrals. So I'm going to talk about how we go about doing this. So for example 1, we're evaluating the triple integral of this function x cubed plus xy squared dv, where E, the region that we're integrating on, is a solid underneath z equals 1 minus x squared minus y squared in the first octant. So if we first draw this out, so let's draw out kind of the paraboloid, right? Remember, this is a paraboloid, and you can remember that because of how the cross sections would end up being 1 minus x squared, which would just, or 1 minus y squared, depending on which way you do the cross section. So it's like a downward opening paraboloid, and it's just the first quadrant. And really, right, the area in which we are integrating over is going to be this kind of quarter circle. And if we think about z, this is at z equals 0, right? So we would say z equals 0, which equals 1 minus x squared minus y squared. And then we get x squared plus y squared when we add these 2 terms over equals 1. And x squared plus y squared would just equal r squared. So this would end up equaling the values of r is just equal to 1. R squared is equal to 1, which means r is equal to plus or minus 1, but we only consider plus, so it's going to be r is equal to 1. We could have negative values of r, but that would just mean r is going backwards, and we don't really need to worry about that. There's no reason to. So we just say r is equal to 1, and this is the region that we're integrating over, r equals 1. So when we're setting up our integral, right, our triple integral, first, look, we can do dz first, right? We can say, because if you think, really you're doing top minus, we're still the same idea of top minus bottom, but for, z, we can just represent this as z equals 1 minus negative, if we factor up the negative, we get x squared plus y squared. This is just equal to z equals 1 minus r squared. So that's our z as a function of r, right? It doesn't depend on theta, right? You could see for no matter what angle you kind of sweep out and go upwards, it just ends up equaling a circle. So the theta doesn't really matter. The height just depends on the r. So for example, if you go like r equals 1/2, it would be kind of half the height. Or if you go r equals 0, it would be the full height. And if you go r equals 1, it would be 0 height, right? Hopefully that kind of makes sense. So we're going from 1 minus r squared to 0. And then the region that we're integrating over is from 1 to 0, right? Like in terms of the values of r, because we're doing d. So we're doing r dz first, and then we could do dr, and then we could do d theta, which is from 0, or pi over 2 to 0. So what are we integrating? Well, it's going to be this. What we can do, let me actually kind of give this some space though. What we can do is we can kind of factor out an x. So we would have x, I can do it here. I'm kind of running out of space. I'm just going to erase this because I don't think we really need it now. But what we can do is we can kind of say, okay, factor out x squared plus y squared. So x is r cosine theta when we bridge it over, and then x squared plus y squared is r squared. So I get r cubed cosine theta times r dz dr d theta. So the first integral is pretty simple, right? There's no, nothing in the integrand depends on z. So it would just be what we have. So r to the 4th, right? Because you multiply the r by r to the 4th, cosine theta. It would just be times z, right? The antiderivative of 1 is just z plus c, from 1 minus r squared to 0, which would just end up being, right, by FTC, just 1 minus r squared. Dr d theta. What we can do really quickly, first of all, we can pull out the cosine theta from this because nothing in here really depends on cosine theta. So we can have cosine theta 1 to 0. We can distribute the r fourth to kind of simplify this. So we would get r to the fourth minus r to the sixth dr d theta. And if we think about reverse power rule, right, the antiderivative of r to the fourth is 1 to the fifth r to the fifth. Or 1 over 5 r to the fifth. And then 1 over 7th r to the seventh. Or 1 over 7 times r to the seventh, right? You just add 1 and then take the reciprocal as a front. So we would end up getting 1/5 r to the fifth minus 1/7 r to the seventh. 1/5 r to the fifth. Okay, yeah, it does work out. Whatever. When we go from 1 to 0 by FTC, the 0 we don't have to really worry about because when we plug in 0, we're just going to get 0, so we don't need to subtract anything. When you plug in the 1, 1 to the 5th is just 1, 1 to the 7th is just 1, so you get 1/5 minus 1/7, which we can pull out of the integrand. So 1/5 minus 1/7 integral 0 pi over 2 cosine theta d theta. Antiderivative of cosine theta is sine theta plus c, so it's going to be sine pi over 2 minus sine 0. Pi over 2 times minus sine 0, 0. And then sine of pi over 2 is just 1. So this is our answer, actually. So it's pretty straightforward, actually. I don't think this is too difficult. It's just making sure you understand what is my bounds, right? Because I need to have z as a function of r, right? If I'm doing dz first, or as a function of r and theta. So let's do the example 2 and kind of work through example 2. Let's say we want to find the volume of a solid lying in between the cylinder x squared plus y squared equals 1 and then x squared plus y squared plus z squared equals 4, which would be a sphere. So if we draw this out, I might even get rid of this stuff. We don't really need it. If I were to draw this out, so I would do something like this, and then this is my cylinder, right? It would extend up, and down, infinite height because it doesn't depend on z. But when I think about my sphere, right? First of all, my sphere has a radius 2, so keep that in mind. So if this is radius 1, radius 2 kind of double that, right? And if you draw your kind of sphere, it would maybe look something like this. And then if I extend it down, I'm trying to find the volume of this part in between, right? So first thing I notice is, well, I can just kind of split this in half, right? I can just find the volume of something in between just kind of, this hemisphere and everything above z equals 0, and then I can just double that to get the total volume by symmetry, right, of this kind of portion right there. So if you think about this, let's rearrange, and we see that, okay, z squared equals 4 minus x squared minus y squared. Hopefully you notice, wait a second, that's minus r squared, right? When I factor out -1, I get x squared plus y squared, so this just ends up being 4 minus r squared. But now I got to take the square root, and this is where I get the plus and minus, right? Well, because I'm worried about positive values of c, anything above z equals 0, I can only consider the positive version of this. So this is kind of like the top bound of my this is kind of the surface that it represents, right? So this is the top surface, and then the bottom surface is just z equals 0. And then I'm only integrating in this region, right? I only want to integrate in that region. So if I think about x squared plus y squared equals 1, that's as simple as just r squared equals 1, or r is just equal to 1. So I'm only integrating within that region, and I'm integrating the full way through from 0 to 2 pi. So what we can say is the volume is equal to 2 times the triple integral. Well, what function am I integrating? I'm really just integrating, hopefully, let me just check if I'm recording. My phone's been doing weird. Oh yeah, I'm recording, that's awesome. I'm integrating z equals, or f of x, y, z equals 1. Remember, in order to find volume, you were just doing the triple integral dv. Remember, if you think about double integrals to find the area, well, you would just do double integral dA, where z is equal to 1. So double integral 1 times dA. Because if the base is equal to the total area and the height is equal to 1, the volume just equals the area numerically. They have the same numerical answer. So we're doing triple integral dv. We're going to do our good old r dz dr d theta. And we're going to go from square root 4 minus r squared to 0. We're going to go from, right, that's the surface that I'm worried about. And then I'm going from, in terms of the polar area that I'm integrating, 1 to 0 and then 2 pi to 0 for the angle. So if I'm doing 2 times integral, so r dz, right? There's no z in here, so this would just end up being r times, in the same example where I'm doing z from the top surface to the bottom surface, it would just be square root 4 minus r squared dr d theta. And what you're going to see in a second, and I know I'm not writing bounds, that's just because I'm explaining. You're going to see in a second, well, if I'm going to try to, let's just do it like this. So I'm going to do from 1 to 0, or 2 pi to 0. Let's do use, to solve this, we can do u sub, right? We can say, hey, u is equal to 4 minus r squared. Du is going to equal negative 1/2 dr. Yep, that looks, or r dr, yep. I have an r dr here, so I just need, I would multiply, and I would, I went backwards. Negative 2r dr when I take the derivative, but I would need to multiply by negative 1/2 du to isolate r dr. So then, what I can go ahead and do is pull that negative 1/2 to the top, or out of the integral. So let's do this. I would get negative 1/2 times 2, which is just negative 1. So from 0 to 2 pi. For our bounds, right? When I plug in 1 here, I get 4 minus 1 squared, that's 3. Right? Yeah, 3. When I plug in 0, I get 4 minus r squared, which is 4. And by, the integral properties, I can switch the bounds and get rid of this negative, right? I can pull the negative into here and then switch the bounds from just 4 to 3. So I get square root u d theta. This just becomes 2/3 u to the 3/2, right? Because it's u, square root u is just u to the 1/2. So you add 1 to the exponent, which gives us 3/2. Put that in front, take the reciprocal, you get 2/3 u to the 3/2. So when I do my fundamental theorem of calculus, it's going to be 4 to the 3/2 minus 3 to the 3/2. Awesome. So then, wait, that's right, right? Yeah, I think this is right. Yeah, that should be good. Okay, so then I would, there's no theta in this, so this is just this is the same as just multiplying by 2 pi, and then I would get 4 pi over 3, and then this becomes 8 minus 3 root 3 when I simplify this, right? If I, when I do square root, right, because this is just doing square root of 4 and then taking it to the 3rd power, so I get 8 in that case, and then same thing here. If I were to take the square root, I would get root 3, and if I were to cube it, I would get root 3 times root 3 times root 3. 2 of those root 3s would turn into 3, so I'm left with 3 root 3. But you can probably leave your answer as this times, 4 pi over 3, 4 to the 1.5 minus 3 to the 1.5. That should work too. But yeah, this has been triple integrals in cylindrical coordinates. So yeah, thank you for watching. Hopefully this wasn't too confusing and kind of reminds you of polar integrals. Yep, thanks for watching.